Hello, everyone. We're glad you joined us on this Thursday afternoon. We'll get started now here that people have had the chance to sign in and download the Zoom app. My name is Lucy Andrews, and you've probably heard from me in registering for this workshop. I'm a graduate student and researcher with CalAdapt, and I'm delighted to present some of my colleagues here today who'll be giving you an introduction to climate science. Just as an administrative note, you're all on mute just so that we have minimal background noise for all of our participants. You have the option to type questions into the chat box, which we'll be monitoring on our end. And there'll be the option periodically for you to take some polls to give us some feedback as to how this is working for you and how CalAdapt has served you in the past. Diving into it, we have two presenters today. The first is Nancy Thomas. Nancy is the Executive Director at the Geospatial Innovation Facility at Berkeley. She's also a Program Manager here at CalAdapt. We also have Owen Doherty with us. He is a climate scientist and in his own terms, a recovering climate modeler. He works at Eagle Rock Analytics based in Sacramento. With that, Owen, I'll allow you to begin. And so feel free to share your screen to get going.
Okay, thanks, Lucy. I will share my screen once you have stopped sharing. All right, thanks so much for your kind introduction, Lucy. Today, we will be introducing climate data on a very high level. I have been absolutely dreading this webinar because all of the topics that we're going to be talking about today really could be full hour-long webinar topics. So it's a real challenge to give you guys a good solid overview that helps you to understand how to use climate data for your own end uses, but actually, gets through enough to be robust. So we're going to try our best to balance that today. We'll be talking about climate model basics. What is a climate model? Why do we do them? What's in a climate model? We'll talk a little bit about the downscaling that takes big climate model data and turns it into localized products that people can use for adaptation and resilience planning. We'll introduce the concepts of climate change scenario pathways and uncertainty in climate modeling and what that means for you as an end user of climate data. I'll very briefly introduce a few common climate variables and kind of let you know where they come from and where you can find them on CalAdapt. And then we'll hand things over to Nancy, who's going to do what I think is the fun part of today's webinar, which will be showing you hands-on how to use CalAdapt to get some of the data that we'll be talking about today. So I am, as Lucy said, a recovering climate modeler. And as such, I am classically trained as a scientist and therefore very forthright and aggressive about talking about deficiencies in the current science and identifying where we could do things better. And that represents a real big hurdle and challenge for communicating science, particularly climate science, because scientists will always talk about what they did wrong and how things can be better. And maybe we have a harder time talking about what we're doing really well. Today I'll be introducing uncertainties and all sorts of things that you could think about as a negative or a big challenge to overcome. But I did want to start with something we're doing really well. And that is that climate models are unambiguously doing a fantastic job in getting the large-scale response to anthropogenic climate change right. This is a paper that came out last month looking at the previous generation of climate models, which were run at the start of the 20th century. Gives us a nice long stretch of about 20 years to look at as to how they've done. And the left part of the graph here shows the hindcast, or how the models did when they were predicting a known climate. And one wouldn't expect them to do really well here because they're often tuned to recreate historical climates. But what one wouldn't know is how well they predict out in the future. And so the black line represents the mean of all the climate models that comprise the previous cooperative climate research. And the red line represents observations of global mean temperature. And you can see that even though we're looking at models that are now over 20 years old, they did a really good job in predicting the first 20 years of the 21st century. And moreover, if you dig into this paper, which is a great read, if you look at some of the original climate models, even dating back to the 1970s, even though they were very primitive in terms of what they could predict, they did a fantastic job evaluating the large-scale trends. So I did want to start with that because I will be talking about challenges in climate modeling and using data moving forward, but broadly, we're doing pretty well. There are lots of sources of climate information, and today we'll be focusing on projections and ergo climate models. But I did just want to briefly mention the importance of observations. And observations kind of come in two large bins: location-based observations, which are often instrument-based single records, and then more broad historical synthesis, which bring together data points and observations of different instruments into a uniformed record. And in CalAdapt, the majority of data that is presented are these historical synthesis, and that's because it's a lot easier to compare a historical synthesis to a gridded climate model output. So you're comparing apples to apples. And this on the right, the figure that's showing here, shows the historical conditions from the change tool that was recently developed, showing the mean temperature from one of these historical synthesis over the period 1961 to 1990. And so, yeah, you should be aware that CalAdapt and any climate data information should offer you historical and future projections. So, climate models are, I guess you could think about as ubiquitous in adaptation planning, but it's interesting to think about why we have them and where they've kind of come from. As scientists, we're very interested in performing experiments. We want to know if we change the amount of carbon dioxide or methane or sulfur hexafluoride or whatever into the atmosphere, what is going to be the Earth system response to that? And this is analogous to your high school chemistry experiments where you sat along a nice big blacktop bench and you had chemicals and you'd add different things in different rates and you'd monitor to see how the reactions and how these chemicals responded to the perturbations. And we do the same thing as environmental scientists who do climate work, but it turns out that the UN sort of frowns upon large-scale experimentation, like, for example, melting the polar ice caps to see what would happen. We really can't do that. So in order to understand what the responses will be to declining ice pack, we have to model it, and we have to come up with mathematical frameworks, put that into computer programming, and run them to see how things will change. And to do this, we discretize the Earth's surface. We break the Earth down into little cubes in both horizontal distance, so in latitude, longitude coordinates at the surface, and vertically from the Earth's surface all the way to the top of the troposphere and into the stratosphere and atmosphere. The distance between these points that we've discretized the Earth into are referred to as the resolution. And the more points on the Earth that we have, the better the resolution, the finer the scale of information we get about future climates. But that does come at a cost, and that is that computationally it's more expensive and the machines run a lot slower the more grid points that we put in. So there's always a balance between more information and the cost to run them. So what goes into a climate model? Well, it's not just the atmosphere. A lot of times, in CalAdapt, we present a lot of atmospheric data as results. But in this example, which is the Community Earth System Model, which is run by UCAR in the United States in Boulder, you can see the different components of a climate model, and the atmosphere is one of them. But the climate model itself is kind of the dark green center coupler thing. That is the controlling the integrations and how moving forward in time, the model is going. And the coupler stores lots of information and then passes information about the current conditions to the atmosphere model, which will integrate forward maybe 6 hours, maybe 3 hours, making a future projection. It'll then share that information back to the coupler, which will then give the information to the sea ice component and say, okay, here's what the atmosphere looks like today. How is that going to change sea ice? And then the sea ice will go back to the coupler and they'll give that to the ocean components and so on and so forth. So you have a fully coupled model with lots of different routine sub-models which are doing fine-scale investigations. And back when I used to do this sort of thing, I was very interested in how the land surface models were interacting with the atmosphere in future climates. And so I thought it'd be interesting to look at sort of what one component of these many component sub-programs kind of look like. And we're not going to get lost in the weeds here, but I did want to give you a sense of what sort of processes are included when we think about a climate model. You might think it's just the atmosphere, but actually when you go in and you look at the various components, there's a lot of detail. For example, if you think about what would this model might do if a little bit of rain fell into it, well, it would try to figure out what fraction of that rain would evaporate. And that's going to be a function of the atmosphere and the surface heating of the soils. What fraction of that water will run off into a river, and what fraction will be infiltrated into the aquifers beneath it. And in turn, how will vegetation use that moisture and heat, and how will that change the fluxes of gases through the surface? It gets very complicated. And these individual components are not only run within themselves, but they're communicating to the atmosphere via the coupler, allowing the atmosphere to kind of change. And over time, we do see this incredible evolution of the Earth's surface in response to changes in greenhouse gas concentrations. And to give you a sense of the minutiae that we can go into here, I used to be very interested in dust, and spent 2 years of my life changing how the size of dust in models and changing how wind interacted with dust and how much dust would be lofted up into the atmosphere and what that would do to the regional climate and clouds and all sorts of things. And so individually, these tiny components, which are fractional, make up hundreds of lines of code, which allows for our simulations to be rich, and it allows for our climate models to do a pretty good job replicating really complicated processes. But climate models are not weather models. There's very big design differences in between the two, and it kind of all boils down to this weather versus climate. When you're trying to model the weather, you're interested not only in how big the change in the weather is going to be, but when that change is going to occur. So you'd be very interested in the timing of when the rain's going to start, how heavy it's going to be, and when it's going to end. You're going to want to know that down to 15 minutes or 10-minute increments, very finite pieces of time. When we think about climate, and climate is the average of weather over longer periods of time, we're less interested in the when it starts and when it ends, but of what is the effects of many of these wind and rain events going to be on the climate signal. And that gets back to the way that these climate models are designed. We look at these individual packages and we can see we're interested in long-term climate change variability and how that is being driven by the ocean, how that is changing the ocean and sea ice and land ice, and how the vegetation will respond and what that will do to the soil characteristics, which will in turn change the heating and the cooling near the surface. So we've got a lot going on, but our focus on these big, slow-moving events means that our models are going to be tuned to generating statistics about the weather rather than actually trying to predict the weather. You're never going to see a climate model, or you shouldn't see a climate model used to say on November 17th, 2076, it's going to be 42 degrees in Sacramento and rainy. That's not what these models are designed to do. But that isn't to say that we can't learn a lot from them. These climate simulations, we may not be able to say that, hey, an El Nino is going to be starting in November 2052, get your rain jackets ready. But if we were to look at all of the 2050 decade, we might be able to say something about what El Nino is going to look like then. Will it be warmer than present conditions? Will they be rainier? Will they be less rainy? Will the rain be more intense but less frequent? These are the sorts of things that climate models can get at. We can understand climate variability, we can build statistics around it, but we're not really interested or capable of predicting the timing and onset of these events. Somewhat related to that is that climate models historically have struggled to really faithfully replicate extreme distributions, so extreme events like really intense droughts or short-term heavy rainfall events. That's getting a lot better. We're making a lot of progress. In particular, the data on CalAdapt right now comes from LOCA, and that was designed to, quote, enable the investigations of extremes. What that means more practically is the bias correction and various statistical tests that went into it didn't focus just on getting the mean right. They were interested in making sure that the distribution shapes were correct, so we can say something about the extremes now. But that's been a relatively recent degree of progress. And even with the progress we made, we should probably make a caveat that extreme precipitation can be tricky to work with. So I did mention earlier the trade-off between computational speed and the resolution of climate data. And this animation here shows sort of the evolution of climate modeling capacity over North America, what has been and what it will be. So presently, we're very close to somewhere between T85 and T104. And if you look at California, you're getting somewhere maybe 15, 20, 25 grid points of information in California. And that's really not enough to meet regional adaptation planning needs. If your grid point includes Los Angeles, Victorville, Riverside, and a little bit of Indio, you can imagine that you're really getting a number of different climate zones in there. And at a local level, unless you find a way to localize that information, it won't be very helpful for planning. So to address that, to get towards the really high resolution that we need, like the more, T40, what you see on your screen right now, we call on something called downscaling to bring the coarse scale information to the local scale. So what is downscaling? Downscaling takes something like the left panel figure here, your Hadley model, which is one of the GCMs that comprises all the GCMs that go into CalAdapt. These are the sizes of the grid cells of this particular model. And after the downscaling is applied in Loca, you can see on the right what resolution looks like. And we use Loca at the direction of the California Energy Commission, which has historically been the agency that's responsible for generating the research and sort of curating the research that goes into adaptation planning on CalAdapt. This process, this Loca approach, which is done by the good folks at Scripps, Dave Pierce and Dan Cahan, provides us with a lot of fine-scale spatial details or contextual details, such as local topography, the ability or your particular local region's influence from the ocean and other mitigating factors. But even though it does provide some context, we can't say that these downscaled finer spatial details are any more accurate. If the climate model that is forcing the downscaled model is poor, the downscaling will be poor too. It will just be showing local features of the poor simulation. And one other thing to note is that uncertainty is introduced in the downscaling. And at present, we don't quantify the uncertainty introduced by downscaling into CalAdapt. There are lots of ways to do downscaling. And so a lot of alternatives to Loca exist out there for you to find and enjoy. There are two large camps of downscaling approaches. Loca is part of the empirical downscaling camp, and that is to say it's a statistical approach. And the alternative approach is dynamic downscaling, which is essentially you take the coarse observations from the global model as boundary conditions or initial conditions, and then you run a finer scale model just over a smaller domain, which is what the figure on the right is showing. And that produces what we refer to as dynamically downscaled data. Now, if you were to talk to an international expert, they would say, particularly folks who are theoretical or statisticians, they would say, you really need to use both dynamically and empirically downscaled model results and compare them if you want to do, really good planning. But we realize that's a really heavy lift. There's lots and lots of data. It's hard to find them, and they may not be on comparable grids, and there's lots of challenges to using it. We recognize that's hard. And in CalAdapt, there is some dynamic data available from UCLA, but it doesn't cover the entire 21st century, so we don't present it in a lot of the tools. If you're interested in exploring this a little more, you can follow the link to data.gov/climate/portals, and there'll be all sorts of downscaled products that you could utilize in your own work. Now, the last basic point that I'll be introducing today is an acronym. It's CMIP. It's a coupled model in a comparison project. And if we go back to our analogy of chemistry on a high school bench, CMIP is the attempt at saying, look, we have a lot of people doing this experiment. We have a lot of slightly different chemical mixes and slightly different temperatures and pressures in the room and all sorts of different, differences that we may not actually be able to quantify. But maybe if we all design our experiment the same way and run it, we could learn something from seeing how the results change between locations, between lab groups or lab bench. And so that's what historically has been done. There are over 30 groups that participated in CMMM 5, which is the current phase, or I guess the last phase, and which is currently on CalAdapt. And there are lots of variables that get produced at very many time steps across a number of resolutions. For the fourth assessment, California's fourth assessment, the resolution was standardized through the local downscaling. So when you go to CalAdapt, the time steps and the resolutions are all fixed, which takes a little bit of work, hopefully, off of your shoulders. At this point, I'm going to turn things over to Lucy and see if there are any questions before we move from modeling basics into talking about uncertainties and representative pathways.
Sure thing. Thank you, Owen. I'd invite folks who have questions at this point to type them into the chat feature. I'll see them on my end. And in the meantime, I'm going to launch a poll that you should see come up on your screen as a way to fill a little bit of time while people are answering questions. So you should see a poll here that asks for a little bit of background about what brings you to this webinar, what your particular domain of expertise or interest is. So feel free to answer that poll and type questions into the chat box. We've received a question, which is about the availability of this recording. When will this recording be available to review? A few thoughts there. First, we'll make the slides available. I'll offer a link to download the slides at the end of this webinar. We'll also be hosting a recording of the webinar on the CalAdapt blog. Nancy, do you have a sense as to an anticipated turnaround time?
It will probably be up next week.
Next week? Okay. For those of you who registered in advance with the form, I have your email address, and I will be sending out a notification to folks that blog post is live with the recording and with the slides linked as well. So you'll get it in a few different ways, but by the end of next week, this will be available for public consumption. Another question, Owen, for you here. Should all data sources we use be of one type? For example, should all data be LOCA?
That's a good question. On a highly theoretical basis, the downscaling technique that you use, LOCA versus MACA versus dynamical downscaling, those represent an additional source of uncertainty. And when you hear the word uncertainty, you think, oh, that's bad. But actually, when we're talking about projections into the future, we want a representative uncertainty that tells us how the statistical downscaling affected the quality of the data. So we want to know how variable, what's the difference between LOCA and MACA? That's very interesting information. It can make your analysis stronger and your statistical tests a little more, I don't want you better, but more fair. That being said, for adaptation and resilience planning, that's a lot of work. That's a lot of work for a city planner to do. You might have to hire a consultant to do it, and a lot of the times it's not worth it. So I would say from a practical perspective, using one is fine, and what is most commonly done. But from a theoretical perspective, obviously more is better.
Great, thank you. How many questions would you like to take at this point, Owen? I have another 2 for you, but want to respect people's time as well.
Yeah, let's just do one more. We do need to kind of keep on, but if there's extras at the end, maybe we can come back and address them.
You got it. Then the next question that popped into the chat box is what should be considered when selecting specific downscaling methods?
One approach which is commonly used is to use the method which was most accurate for your region and variable of interest. So if you're in Orange County and maybe you're in Santa Ana, there may be a particular downscaling approach which replicates the complex and rapidly changing topography from the hills through the canyons right down to the ocean. So the one that historically was most accurate would be a really good starting point for looking at future projections.
Sure thing. And then to follow up, when folks are curious to know what's been used in their area for their variable of interest, is there an easy source of information, or does that require a little bit more background research?
I'm not sure exactly what the first couple words implying, but if you're looking for a particular variable that has been done, the CalAdapt database kind of has all of what has been downscaled by LOCA available for you to look at. And then if you follow the link to the data.gov that is in the PowerPoint, it'll have sort of an overview of what other alternative downscaling approaches has made available.
Fantastic, thank you. I'm going to close the poll that was running. Would just like to report back that of the 60 or so folks that answered the poll, a plurality of people are either here out of general interest or because they work in or are interested in land use, community development, and natural resources. So just fun to hear that. Thanks for participating, everybody.
Well, awesome. I'll try to address those topics a little bit more. We're going to segue into uncertainty and climate pathways. And I think, speaking a little bit for the CalAdapt team, a lot of times people will come and say, hey, I'm interested in understanding how, say, temperature is changing at my particular location. How do I go about doing that? And maybe we'll start explaining, oh, this is what the climate models are, and here's all the different sources of uncertainty, and here are the two scenarios that the state kind of recommends, and here's the background and why you should do that. And people say, oh, thank you so much, that was really great. Can you just give me a number for my spreadsheet, because I got to put something down here for 2050? And that will of course cause scientists to hem and haw and get extremely uncomfortable. And we're going to talk a little bit about why that is and what we can do to kind of get past this. Climate projections are less than perfect, but that doesn't mean that we can't use them for planning. And there's a good analogy here, which I'm shamelessly stealing from elsewhere. But let's say you are trying to plan a trip and you are about to get in your car and you bring up Google Maps or Waze. It may tell you an estimate of when you're going to get there. It's going to look at right now, what's the condition on the road, how many drivers there are, and it's going to take you 28 minutes to get to your destination. And we know that that isn't a perfect estimate. And it's not perfect because we don't know what people are going to do. We don't know what accidents may happen in the future. But it's a really educated guess, and it has some constraints on historical data, and there's lots of good reasons why that projection exists. But you might tell your friend, hey, my ETA is 28 minutes, and I'll see you then and there. But you don't know that you're going to get there in exactly 28 minutes. It's still information you can use and plan around, but it's not perfect. How do we take our climate projections, which are likewise pretty good but not perfect, and use what we know about the historical uncertainty to improve our utilization of imperfect data? That's the big question. And the challenge is, of course, that there's complexity and ergo uncertainty from both natural systems and the components that we talked about in climate models, but also because, we don't know what people are going to do. We don't know who's going to be president in January of 2021 for the United States. We don't know who the governor is going to be of California in 2024. And we certainly don't know what fraction of people are going to be using heat pumps instead of natural gas in 2035. So we have to make some estimated guesses and try to figure out, okay, here's what probably going to be emitted into the atmosphere, but we don't really know. There's a lot of complexities and degrees of freedom that we can't account for, but we can try. So there is a lot of inherent uncertainty in climate, but we have really good confidence in our understanding of the underlying physics, and we know broadly the directions that human activity can go. We can either change our fossil fuel use or not. And that's enough to make decisions. It's not going to be perfect, but it's enough to start with. And I'm going to introduce a premise that some folks may have already seen. It comes from Ed Hawkins, and it's he calls it the Cascade of Uncertainty. And so starting here at the top, we deal with our uncertainty about the future. We don't know what society is going to look like in 2070. We don't know how well technology will have been shared. We don't know how well people will be cooperating. We don't know what adaptation techniques and new technologies have come out. We don't know, but we can plan for some outcomes, and that's the first triangle of our uncertainty. From how people are going to behave and how society is going to change, we can then start to estimate, okay, here are some possible ranges of greenhouse gas emissions. This is how much CO2 would be associated with the future where we do nothing to address climate change. And here's some CO2 emissions that may be reasonable if people really, really aggressively change their behaviors. And we funneled that additional uncertainty into climate models, which do faithfully represent the Earth, but each has slightly different estimates and calculations and so forth, and it makes our uncertainty even a little wider. And then when we get to the green, that's our regional scenario. We don't know how our broad coarse climate predictions are going to be felt on a super local level. And the blue line represents about what you will get out of CalAdapt. You will get an estimate of how the future pathways, how future societies change, how that will affect greenhouse gases across the models, how uncertain are we of things, and a little bit of regional uncertainty, but not a full amount. And then from there are additional tiers of uncertainty which really segue from physics and climate modeling and the Earth system to more adaptation and local responses. And if we think about this cascade of uncertainty, and kind of break it down a little bit into more how we're actually doing this, you may start to understand how climate modelers are thinking and doing. So this cascade of uncertainty on the x-axis and across your screen is ranging from the potential changes in global temperature from 0 centigrade to about 6 centigrade. And here on the top tier, you can see what we're calling RCPs. These represent the potential pathways for human activity and socioeconomic development, which feed into various models, which are then run in various experimental configurations where we perturb little itty bitty bits of the model and see how it changes the potential outcome. And then here on the kind of the y-axis, you see over time. And so you can see how the different pathways lead to different model results, in which we perturb in different models, and it gives us a range of outcomes of between 4 years ago to 25 years in our future. We can expect the global temperature change somewhere in this range. And then when we move out in the future, our uncertainty grows because our pathways of emissions grow, our model outcomes increase, and our experimental permutations kind of increase it even further. And by the time you get to the end of the century, our outcomes are even less certain. Our certainty is kind of declined. But that's not to say, again, that this information is not useful. You can start to plan with this, but we do have to keep in mind the uncertainty that's sort of introduced. Now, in the case of CalAdapt and the broad way that the state is kind of thinking about things, we are presenting the red lines and the blue lines primarily, and that's the RCP 8.5 pathway, which I'll talk about a bit more, and the RCP 4.5. These are the two pathways that the state guidance is starting to direct people to plan around. You can see also that there's this RCP 6.0 and this RCP 2.6, which have slightly lower different impacts. Right now, those are things that you can consider in a planning perspective, but it's not as officially mandated by the state. So what are RCPs? RCPs, the numbers that you see at the end of it, represent the targeted radiative forcing, or the amount of heating into the atmosphere that we expect to be possible. So 8.5 represents 8.5 watts per meter squared, and 4.5 is 4.5 watts per meter squared. And to generate these future scenario pathways, we take our estimated warming, we break it down into the concentrations of greenhouse gases that it would take to get there, and then we break it down to emissions over time that would bring us to these future conditions. We pass that to our Earth models, and then we get climate results, climate projections from them. And these scenarios are socioeconomic pathways that represent projections. They're not predictions because we really can't predict what people are going to do, how governments and people are going to change. So they just represent potential ranges of outcomes. And here you're seeing the red is the projected global temperature response to RCP 8.5 over the 21st century, and the blue is the more middle pathway, and the green represents the RCP 2.6, which would represent really aggressive adaptation and changes in behaviors, which we really aren't seeing. And then the black is the range of historical observations, and you see them falling within broadly the model pathways. So thinking about our cascade, the RCPs represent the human activity, and then we go down to the next tier, which is uncertainty that comes from models. And these are the modeling groups that come from CMMM 5, that contributed to CMMM 5, and you can see that there's a lot of different groups or 32 that we use in CalAdapt. And they're well globally represented. And with CMMM 6, there's a modeling group effort coming from South Africa. So even all the continents are represented, which is great. And this large wide range of models means that we have a pretty representative degree of how the model construction will impact our climate signals. So on CalAdapt, if you go to a tool, and Nancy is going to show this in a little bit, it's going to bring up a set of these models, by default 4, which have been identified by the state of California as priority models. And these models of the 32 were so chosen because it was thought that as the 4th assessment was being generated, that asking people to look at 32 models was going to be too hard, and it would push people outside of what adaptation planners can actually do on their own computers. So 4 priority models were selected. One represents the warm and dry future climate, the kind of extreme outlier. Another represents the coolest and wettest of the 32 in California. And then there were 2 that were chosen based on how it did historically, what came closest to correct in California. Then there are 6 additional models, which for a combination of historical skill and future outcomes were thought to be good to include. So this is what CalAdapt will pre-populate. It's a nice jumping off point if you're just getting started. You can use these 4 models. But these were chosen based on statewide metrics, which may not be appropriate for your particular location. So best practices would be to assess the model skill at your location historically and the spread at your location. And this work was led by the DWR, the Department of Water Resources, and they're concerned about water availability and across the state. But if you're a program manager in Southern California, you may not actually care about how good a model was in the Northern Sierras. You might want a model that was better in Southern California. And CalAdapt has all the data for all 32 models on its server, which you can get. It can be a little more challenging, but if you were designing a study to be most theoretically excellent, you would want to test the models in your location. And the third tier of uncertainty in our cascade is the uncertainty relative to what Ed Hawkins calls realization. Essentially, each model can be configured in slightly different ways, and an ensemble of models is usually run on the CMMM studies. So we might have the SESM model, which we talked about, and it might be run for the RCP 4.5 and the RCP 8.5. And then that model itself for each run will be, for each RCP will be run 10, 20, 30 times. And each time they run it, they may change the initial conditions of the model or change the physics, the parameterization, and the different nuts and bolts and the knobs and levers that go into the model. And they'll run it over and over again. And this uncertainty, this realization uncertainty, represents how model tuning can affect the results. And if you look out into the future and break down uncertainty into the components that we've talked about, the green is representative of the envelope that is human behavior and different emissions pathways. Blue represents the differences between model groups and different contributors to CMMM. And then the orange in the center represents the internal model variability. So by changing the knobs and levers a little bit or using different initial conditions, how do the model results change? And you can see that what terms of the realization, these ensemble uncertainties, over time becomes a small fraction of the signal, but actually present, it's pretty large. Whereas in the future, the majority of uncertainty isn't even a function of the models themselves. It's a function of we don't know how human beings are going to behave and change our behaviors. I think this is a really interesting figure because it kind of puts things a little bit in perspective about, yeah, models aren't perfect, but really, people are the biggest source of uncertainty into the future. So how do we represent uncertainty on CalAdapt? Well, based on the design of the 4th assessment, we don't have all the information. We don't have the realizations. We don't have the regional downscaling uncertainties to include. So what is done is the modeled variability is shown in kind of outlined in gray, which represents the range of all annual values across the 32 models. Gives you the blue cone of uncertainty is what is represented on CalAdapt equivalent. So I've talked a lot about uncertainties, how they're a critical and necessary component of climate modeling, but how do you kind of use uncertainties in decision making? Well, here are a few kind of points. I'm a little behind on time, so I'm not going to go through this in full detail. But the key point is that there are a lot of different sources of uncertainty, and it changes over time. And how you would use it would be kind of a function of what question you're asking with your particular project. If you're planning for a 30-year time horizon, you might be able to, not worry as much about the RCP differences, because it's all going to be models at that point, but later on your questions and answers might be different. Going to give a quick plug. Planning is underway for the next generation of information that will be available to people who are working in the climate realm in California. Presently on CalAdapt, we have CMIP 5 data, and it supports the 4th climate assessment for California. In planning now is how to use and bring on CMIP 6 and the 5th assessment products. If you have an interest in this, or your organization has a strong perspective of what sort of information should be made available, you can submit comments to the California Energy Commission through this link, and let them know what your needs are for climate data in the future. Because I'm running a little bit out of time, I'm going to talk real fast about CMMM 6, but the state guidance kind of suggests for adaptation planning that we focus on RCP 8.5 and RCP 4.5. And in CMMM 6, there's an effort to kind of parse out a little bit of the radiative forcing from the socioeconomic development that goes on. However, the priority 1 tier groups, there is an analog for RCP 8.5, which is here, and RCP 4.5. So according to state planning, at least, we will have in CMMM 6 a good analog for our historical approach. And CMMM 6 is live, and the data is being updated and made available right now on the Earth System Grid profile. But it will take us some time to bring it into CalAdapt or whatever the state chooses to provide climate information in the future. So now I will take another quick break and turn things over to Lucy for a couple more questions. Or maybe
Sure
not
thing.
for too far behind.
Well, Nancy, I think it might be best if you run through CalAdapt as people are thinking about their questions, and we take questions at the end. Do you think we should go that route, or would you like another round of questions now? I want to make sure you have enough time.
That sounds fine. I think Owen might have a few more slides.
Okay.
Which we should probably finish up first.
You got it. Then in that case, feel free to type, again, more questions into the chat box. I'm going to launch another poll as people are submitting their questions, and you'll see that pop up. This one is about how you use climate data such that we can continue to develop our CalAdapt tool to meet your use needs. So Owen, here is the question from our first submission. What are the best or most accepted public sources of data? And correspondingly, are there any sources of data that are not credible and should be avoided?
That's a really good question. And the sources of data that you use kind of depends on your end use purposes. But broadly, if you're looking for raw CMIP data, use the Earth System Grid. That is the official portal. And it will have all the CMIP variables. If you're within California and you're trying to conform to kind of state approaches, LOCA seems to be preferred, and we know it's reliable. And Nancy's going to describe how you can get LOCA and other data off of CalAdapt in her section. In terms of what to avoid, as long as you're getting it from a .gov or a .ca or CalAdapt, you should be okay. If you're getting it from commercial places, you need to be thoughtful about the data quality that's going in.
Gotcha. Thank you. Another question then is about combining models. You've mentioned that the RCP parameters that we're working with are themselves representations of socioeconomic conditions. Do you mind offering a little bit of commentary on what it's like to combine climate data with other forms of social or economic data to take physical outputs and plug them into, say, some kind of social model? That was just a question that came up.
Very briefly, I won't say too much about it because it's a little bit out of my expertise range, but you just want to make sure that the locations from the climate models line up with the locations of whatever socioeconomic data and model you're using, and that the time points line up. Then using the RCP that most conforms to the assumptions that go into the socioeconomic data that you're using, making sure that you're using the most appropriate analog, which may not be 8.5 or 4.5, it might be 6, it might be 2.4. So you kind of got to think about matching the two sources as closely as possible.
Great, thanks so much. Those are the questions we've received so far. Continue to type stuff into the box, folks, and we'll get to it as we're able. All right, Owen, we'll turn it back over to you.
All right, I'll try to wrap up very quickly because I want to leave Nancy with at least some time to talk. The last section talks about what are the common climate variables that you might see. And the little graphic to the right represents on the CalAdapt download tool, the variables which are immediately available. And you may not, and when you look at this list, immediately be able to tell, but some are from LOCA, which is from the GCM pathway, which you talked about before. And another is from, some others are from VIC, which is the variable infiltration model that looks at the hydrographic and near surface water conditions. And VIC is forced by LOCA. So if you're thinking about our uncertainty cascade, it is one below regional scenarios. It's a model which tries to understand how water surface hydrology is changing in response to climate change. And from that, we get things like base flow, evapotranspiration. I think the snow water equivalent and stream flow are also from VIC. And this is sort of a model that is run off of the LOCA, so it's a degree below. So some of the variables like temperature, precipitation, humidity, wind, that's coming directly from LOCA and GCMs, and the other stuff might be coming from another layer of modeling with its own uncertainties. And here's a list of the VIC model data that's available on CalAdapt across the state, which you could grab if you were looking at that sort of thing. But I did want to talk very briefly about anomalies and why you should think about using them. Climate anomalies are deviations from a historical baseline, typically a 30-year period of historic observations. And it's a way of representing the future projection as a difference from history, which might be more useful and more easily understood by most users. If you can, and you have the expertise to do so, it's always good to couple that difference with a measure of how rare it is, some sort of deviation, looking at the variance associated with it. So here's a graphic from the recently released Maps of Projected Change tool. And here we've highlighted the change from historical database tab. And so that's showing you climate anomalies. And here's in degree Fahrenheit for end of century for the RCP 8.5. So this is the change in average annual maximum temperature across the state. So this represents an anomaly, and it's pretty well and easy to be understood. Look in the Central Valley here, we're looking at maybe 8 degrees Fahrenheit warmer than it was in the end of the 20th century. So it's easy to understand and nice to use. In terms of common variables, I'm just going to talk about temperature real quick because it is most commonly used. It is also the most reliable variable on average in GCMs because most models tune to it. Temperature is usually presented in either an average, which is the maximum and minimum for the day divided by 2, or the max and the min. And then there are various ways of aggregating. So you could be looking at the maximum temperature in a given day, in a given month, in a given year, and that's how temperature is represented. And I'm going to close with a few slides on best practices in using climate data. I always cringe and get nervous when people ask me to talk about best practices because I think about it the same way that a doctor thinks about it when someone asks, how do I get healthy? How you get healthy is a factor of many things, your lifestyle, your food choices, your metabolism, your mental health and mindset. And so if you ask a doctor, well, how do I get healthy? They might say, well, the best thing to do would be eat less Cheetos, get off the couch, or something along those lines, right? And it's kind of the same thing for using climate data. I can give you some high-level things that you may have heard before, but your best practices really refer to what you are doing and the variable you're using and where you're using it. That's going to inform your design. But nonetheless, we develop good practices because having frameworks helps make decision support in the policy and economic realms more achievable. And adaptation planning to avoid climate impacts is a function of how credible the information is, and by using and referring to best practice, we can minimize bad approaches and have a little more credibility. So these are graphics that are taken right off of CalAdapt from UCLA, but look not only at model average projections, but also individual models. Think about that cascade of uncertainty and look at the models. We need to know each of the individual models, their contribution in addition to the model average, to be as robust as we can be. And again, here it is. You know, if we look at the models, you see a huge degree of spread across them, and understanding how you know, the average might be here, but your range across the models is there, and that's very helpful to know. You want to select long time periods for most useful information, usually periods over 30 years. If you ever see someone like asking for, hey, what's the temperature going to be in 2050? Use that as your time point. You should cringe. You should be worried, because these climate models, again, we're not trying to replicate any individual day or week or month. We're trying to get representative conditions over a time period, the climate, the 10-year rolling average, any time point. So instead of looking at what number represents 2050, maybe the average of the 15 years before and after 2050 would be better and more informative. And there are lots of different ways to calculate these averaging. Fresh through it right now. And again, this refers to those uncertainties. And the last is just always remember that these future climate projections are not weather predictions. They need a longer range of time to be made actionable. And I will hastily turn things over to Nancy in the hopes of giving her some time to do a few demos.
Thanks, Owen. If you stop sharing your screen, Nancy can share hers. And as Nancy's booting her computer onto the webinar, I wanted to answer one question, which is, where are these webinars hosted on CalAdapt? The answer there is they're hosted as blog posts. So if you take a look at the CalAdapt website that Nancy's put up here on the screen, in the upper right, you'll see a tab that says blog. If you click that and then scroll through, you'll see information about new tools and those sorts of things, as well as webinars posted, for example, accessing climate data through CalAdapt there.
Great. Well, thank you so much. Thank you, Owen, for that information. And I do want to reiterate that Owen's presentation is going to be made available. So I know he had to run through a few of those last slides, but no worries, you will have all of those slides available. So in the interest of time, I'm just going to do a really brief introduction to CalAdapt. I know some of you on this call are already familiar with the tool, but what we do at CalAdapt is our goal at CalAdapt is to make this climate data that Owen has been talking about useful and actionable for people. So we really want to make this data available for a wide variety of different users. So we do that in several different ways. We have climate tools on CalAdapt, which I'll show you a little bit more in a minute, that allow you to sort of easily interact with the data, and you can slice and dice it in many different ways. So you can look at an area of interest and get charting and graphing tools. You can also download data directly. So some people just want to come to CalAdapt and really grab the climate data that Owen's been talking about and do their own analysis. We have tools that make it easy, again, for you to sort of grab the data that you're interested in, so the time period that you want, the location you want. And then we also have an application programming interface, so a web API. And the web API really allows you to really customize the data set that you're interested in. And that requires a little bit of programming skill. So if you have some ability to write Python code, we have some R packages that are coming soon. You can then go in and really tailor the data that you're interested in to your application. I'm just going to quickly go over some of the tools. So this is really the easiest way to sort of jump in and start working with the climate data. So we have many different tools that look at different variables. Owen mentioned the temperature, precipitation. Those are the key local variables that are in the annual averages. We have extreme tools that look at extreme precipitation and extreme heat. And then, of course, we have many other variables: sea level rise, snowpack, wildfire, stream flow. So I really recommend that if you're interested, come to CalAdapt, cal-adapt.org, and start playing around with these tools to see what type of stuff you're interested in. I'm going to really quickly show you our latest tool, the Massive Projected Change. This is what Owen had been showing. This is really our tool that we are intending to make sort of the easiest entry into looking at climate data. So within this tool, we already average the data over these 30-year time chunks, so you don't really need to think about that. This tool is also showing an ensemble of the 10 different models that Owen was talking about. When you look at the tool, you initially get some information about what the data sets involved in the tool are. You can hover over them for some more additional information. So what the tool is doing is looking at 30-year averages of a historical time period and then a mid-century and end-of-century projection. So again, in the interest of time, I'm just going to quickly go over this tool. So up at the top, we can choose which of these three main variables to look at: max temperature, minimum temperature, or precipitation. Right now, we're going to stick with maximum temperature. You can look at, you'll see that the default is the historical baseline. We could also choose to look at these different time periods. As in all of the CalAdapt tools, we can look at both RCP 8.5 and RCP 4.5. So for example, if I want to look at mid-century RCP 4.5, I can select that. And I can also click on this map to look at the actual values for the points that I'm interested in. One thing you'll notice is that the data is in C. One of the things you can do with this tool is change the units. So I tend to be more familiar with looking at Fahrenheit. So I can change that in the tool, and then that's now what will show up. So a couple other things about this tool. You'll see that we look at absolute values is what we're looking at right now. We can also look at the change from historical baseline or anomalies, as Owen was talking about. So if we click on that, what we now are getting is that change from the baseline temperature. So when I look here, I'm looking at a mid-century RCP 4.5 value. That's an increase of 4.1 Fahrenheit over the historical baseline. A couple other things we can do with this tool. What I think is most interesting is on the bottom left here under the controls, you can look at the swipe view. So what this allows us to do is to actually compare multiple time periods and multiple scenarios within a single viewer. So you'll see you can actually use this scroll button to look at these different scenarios. And now you'll see you have two controls. You can pick whichever, what you want on your left map and what you want on your right map. So let's just start by comparing mid-century RCP 4.5 to end-of-century RCP 4.5. So what's that projected to look like between those two time periods? So again, you can look at either absolute values or change from historical. And a couple other nice things that you can do with this are you can actually start comparing different locations. So I can click on Sacramento, and then perhaps I want to look at Fresno, for example. So now I actually can look at how those two different locations are expected to change both for a mid-century time period and then an end-of-century time period. And another thing that is really interesting to look at is the comparing 4.5 scenario, which is really sort of a lower emission scenario, to the 8.5 scenario, which is a higher emission business as usual. So for example, if I want to look at the end of century results, on my left, I can have end of century RCP 4.5, and on the right, I can look at end of century 8.5. And this is where you really start to see some dramatic differences. I think this is a really interesting way to look at the data. it's really dependent on what we choose to do as human societies as to which of these futures we might expect. And again, you can start to dig into the data and really compare different locations and see what some of these numbers are looking like with this higher scenario. So now we're seeing in some regions, we might see an increase in 9 degrees or more by the end of century with an 8.5 scenario. So it's a really interesting tool to play around with. And with all of our tools, you can change the boundary. Right now, we're looking at grid cells, but we can also aggregate by many different boundary layers, and we can compare the results that way. We can also look at the data and export the data itself. So this is how we really try to make data useful for a number of different audiences. So in this tool, you can download the image itself, if that's something, and the legend, if that's something that you want to put into a report, for example. And you can also download the data itself. So in this tool, what you're downloading is raster data. So this would be a TIFF file. Let's see, let's close that. So there would be a TIFF file, which you could then input into a GIS package. Other of our tools allow you to download tabular data, which I know is really important for a lot of users. So we are going over time. I just really want to quickly show you that under this data tool, this is where you can actually just directly download the data without going through the process of looking at charts and graphics and visualizations. And you can look for individual climate variables. Again, we host all of these different variables, so you can select what variable you're looking for. And then the user chooses whether you want to download a raster data set, so if you want to input this into a GIS, or if you want to download a tabular format. And then you can slice and dice that data in various different ways. So unfortunately, I do think that we need to move on. I really ask that if you're interested, play around with these tools. We're really interested in hearing your feedback. So I want to point out just a few things on the website. There's a lot of information about using our API. So if you want to do your own coding, you can get to that on the main page. We also have a newsletter. The newsletter, we send out announcements about new tools, new data, and upcoming webinars. So if you're interested in that, please do join the newsletter. And then I also want to show you, we have a survey. We're sending this link out to the webinar, but you can also get to the survey on CalAdapt itself. And this is really helpful for us to get your feedback. What types of tools are you interested in? What types of data sets would you like us to see us showcase on CalAdapt? So hopefully you can answer some of those. And with that, I'll give it back to Lucy to sort of wrap up here.
Awesome. So I just sent you all a link in the chat box to that user survey that Nancy mentioned. I'm also about to drop in a link to the slides that Owen has put together for us. We encourage you to stay in touch, particularly if there's some way in which CalAdapt can support you in your climate adaptation work. We're always looking for suggestions for new tools, and particularly for beta testers who want to plug in, roll up their sleeves and help us design our products for the wider California community. So with that, thanks so much for your time. Thanks even for an extra 5 minutes. We hope you have a great rest of the afternoon.